Hey, welcome folks. Thanks for joining. Today we'll kind of go through several notebooks and some new ideas, some of which work and some of which, at least as you'll see, don't work for me. Maybe various reasons which we will get to discuss. So first off, we'll be starting with actually implementing cosine scheduling for the noise, cosine noise scheduling, which, if you recall, Jeremy had briefly touched on in this particular notebook, DDPM version 3. Traditionally, what we have used, implemented so far, is a linear schedule and with a beta min and a beta max. And he changed the beta max from 0.02 to 0.01, and that enabled him to get most of the benefits that accrues from using a time schedule. But there are some additional reasons why switching to a cosine schedule would be interesting, and he does that in the paper that we are, or in the notebook we are about to discuss. The cosine schedule basically changes or eliminates the total time value, which is the capital T of the alpha bar equation. So this is the alpha bar equation where time step small t as a function of the capital T is expressed as a function of the capital T and then multiplied by pi over 2, and then you take the cosine of that and square it, and then use that with just a fixed number of steps, which continues to be 1000, to generate these values where A is used as alpha bar is AB, and the sigma value is 1 minus alpha square root. And these, in turn, are very similar to what we have seen before in terms of graphs. The linear schedule starts with beta in terms of adding the noise, if you recall. So the low noise to start off with when our image is x0, and then we end up with almost all noise at the end of 1000 steps. This is the forward function noise addition. Then we go to how to extract sigma from this, and then the alpha bar. And alpha bar is for the noise extraction process, if you will, where we start with the heavily noised image and then go to the denoised image. And as part of his comparison of the cosine schedule, he also pointed out that alpha bar plot, it's very steep. It's not as smooth as the cosine curve. And the slope of the curve is important when the slope is all over the place, whereas this orange curve, which is the slope of the cosine schedule, is rather smooth. But then he indicated that just by changing the beta max to 0.01, he got most of the benefits. So in this notebook, he just changed beta max to 0.01 and stuck with it. Unlike
what was capital T here?
The total time. That's the total number of steps. So capital T is 1000, for example.
Okay. And the small t is the number of steps, the time step at a particular instant.
Yeah, is it steps that you are taking at any given time, right? So you say step 50 of 999, you start at 0, then small t is 50, and 1000 is your capital T. So that's how that used to work. But now we a couple of interesting things that I encountered during the week. It was kind of frustrating because all of this used to work when I played with it earlier. And then I believe, I'm not still sure of what you said, Mayank, of a new version of diffusion, although somebody else also pointed out that that might be the root cause. But the issue is when you install Mini AI, it actually automatically installs a diffusers. and the diffusers library does is 0.21.1. I don't know whether that has changed recently, but something has changed in the Hugging Face diffusers.
Yeah, recently diffusers library was updated. I had seen it in the couple of tweets. So, one of the DevRels at Hugging Face who works on this diffusers library, he had made some changes. Uh, the whole team has made some changes, so I thought it might have that bug might have resurfaced.
Yeah, except I mean, this is what something has changed, that's for sure. This is automatically what it installed. But anyway, a couple of things that I would like to point out is one, for these notebooks, I found the need to install KDiffusion independently, otherwise some things fail. And as I pointed out before, you need to comment this out, otherwise it runs on CPU. I think this is environment specific, that Jeremy has multiple CUDA visible devices in his when he's running, but not relevant to us. Otherwise, CUDA doesn't get used. So you need to comment this out, install this. And in order to avoid my UNet 2D imports fail to work, and interestingly, when you debug, that's a prior problem that existed. But it's been reintroduced, it seems, due to some changes in the diffusion library that the maintainers were making. So you have to install transformers as well to get around that problem. But once you fix that, things are working. But I wouldn't say normally, because as you see, something that works in the next notebook, some things that work for Jeremy absolutely become rubbish, at least for me. So I haven't bothered to debug it yet, but I'll we'll encounter that when we run discuss the next notebook. I'm not running the
Similar
notebook.
things happens with me too. The FID scores are quite rubbish at my end. So he was having 3 or 4 FID and I was getting 15 or 17. So that was the kind of variance that the FID score was.
That is still accurate. It's just that is, I think, due to some mistakes he had in the code. So once those were fixed and the current notebooks are run, the FID scores in the range of 15 are appropriate. That is the actual value. And you'll see we get to 3 as well when we go through today's discussion. But what I'm talking about is a specific research project that he implements, which turns into rubbish. Strangely enough, it used to work with me in the about a week back, and which is why it was frustrating. Starting about middle of last week or middle of this week, I should, well, depends on how you count, but around Wednesday last week, or Wednesday last, it stopped working. And I had to install the transformers to get it to work again. And the latest version of the diffusers library seems to have some problem, or it may just be that they fix some issues, as a result of which, at least what research he's doing in the next notebook turns out to be somewhat meaningless. But we'll take a look at that when we get there. So in this notebook, as I said, he's implementing the cosine schedule, noise schedule. So all the front of it is the same as before. But the bottom line, he just says, we are trying to get rid of this concept of, capital T. And now, in a way, it's interesting because at the end of the day, you still retain the notion. It's just that you don't have to struggle with 2 values. You just kind of stick with 1 value. So the simple thing that we do is alpha bar is defined this way, as I already showed you in the other notebook. And then one of the advantages of alpha bar being defined in this particular way is that you can also do an inverse alpha bar, because if you know alpha bar as a given specific equation, obviously you can invert the equation to get back to the inverse alpha bar as well. But he also thinks of this as, with the diffusion idea being new, people were kind of trying with the way it worked, and then you begin to kind of distill the idea so that you kind of break it down into its essentials. And so we were thinking, or we saw that in the DDPMV3 paper, or notebook, which I just shared, we were implementing T by T, which could be 500 or 1,000 steps. And that we just used the change of Betamax, as I showed you, we just changed it from 0.02 to 0.01, and that gave him most of the benefits. Now here he's saying, let's get rid of the number of steps and the concept of number of steps and the total time steps T. Instead, just assume that the value lies between 0 and 1, and the T, or the small t that we are looking at, is just a fraction of the way that you have gone between 0 and 1. Right? So we just assume that small t is nothing but a percentage we have moved between 0 and 1. So that tells us simply what percentage of the diffusion process we have moved through. Right? And 0 would be a clean image, and 1 would be all noise for the forward diffusion process. So when we think of it this way, then alpha bar is not something that you have to look up out of 10,000 or 1,000 steps and stuff. It's just some value you calculate. And because it's a value you calculate, you can inverse calculate it as well. Right? And you use this noisify function remains the same. The only difference is that small t just becomes a random float between 0 and 0.999. So that, again, if you think about it, it's just nothing but, you know, some value between that you choose among 1,000 values. But you calculate alpha bar as just a function. You just use the definition of alpha bar shown here. And because a cosine function is used here, that's why this is a cosine schedule. And then the rest of it, like xt, is again alpha bar t square root of that multiplied by x0, and then some amount of noise. Right? So that definition remains the same. It's just how you calculate alpha bar that changes, and alpha bar is now a value that you calculate rather than look up. I mean, it doesn't really matter, but the bottom line is you just think of it as a percentage of the diffusion process that you've been through. Now remember that this will become an important source of a long discussion. Most of our discussion, in fact, today will kind of center on this. But if you recall what happened, he originally tried the value here. It was this tensor of values multiplied by 2 and then subtract 1, which gave us the range between -1 and 1. But then he found out, and he had the discussion in the last notebook, he found out that, you know, everything worsened, nothing worked, because originally the distribution was between 0 and 1. He fixed it to say, oh, image distribution should be between -1 and 1, and things stopped working or things got worse. And then he figured out, oh, maybe I shouldn't worry so much about the fact that it's everything should be between -1 and 1 or a range of 2. Maybe the range is important, and I should retain a range of 1, because the original set of images he was working with and that he had a bug on, but which worked well, the range of values was between 0 and 1. So he thought that the range, he thought that the range of 0 to 1 is important, but let's still center the value. So we can do that by subtracting just -0.5. So the range of values that we now have for the tensors are between -0.5 and 0.5. Now, all this was just debugging himself with no kind of theory or logic behind it. He just realized that he had a bug in the code, and when the original values were between 0 and 1, tried to get it to what images typically are, which is between -1 and 1. That didn't work, or it stopped working. And so he kind of then shrunk the range to -0.5 to 0.5. So that's where we are. And today we learn why this range of value is very important. But that we'll do in the next hour and a half. But right now, he's just focusing on the cosine scheduling of the noise. So now we have, what he does then is say, as part of the cosine schedule, I've already mentioned that we just look at it as how much along the path between 0 and 1, or what percentage between 0 and 1 we've gone through of the diffusion process. So if our value is 0.05, that means we are 0.5% of the way through the diffusion process, of forward diffusion, that is adding noise. So then you can see this as an indication. He just uses the same technique of just putting in the labels. So these are images which have been noised by these amounts. So you can see that when it's 5% noised, these two images are fairly still clear and observable. 25, 35, you can still see it. At around 0.75 or even earlier, like 0.65, above 0.45, you can barely see what it has. Even at 0.3, you can see at 0.95, 0.75, 0.65, it's all pretty much all noise, right? So this is an interesting image, because you can now see, as you add noise, excuse me, where you end up with the images, with what fraction of the forward diffusion process you're through. So when it's about 60%, you can see how much noise there is. Underlying image obviously is different for each image in the batch. That is, the clothing element is different. Then you go through the callback function, fitting process, and everything is the same, and you train the model. Now you're using the cosine scheduling and using that, the newly trained model, to again predict the noise in the training the model to predict the noise. And then you go through the sampling process, you save the models, and you can now create a denoise function, right? Where you take a batch of noisify data and denoise it. Now we know T, which is different for each element in the batch, right? Because each element has a different percentage that it's been through, as we saw here. Some elements are 5%, some elements are 60, some are 35, some are 30, blah, blah, blah. Then you try to denoisify the image, and you just kind of write the inverse equations to denoisify. However, you add this clamp in the values, and then you show the images and see how well the denoisify function gets you back the images compared to when you had the noisify, right? So you can see they're pretty close, because you're just inverting the process. You have 0.05, 0.25, 0.35, and you can go back and forth and compare. Now, interestingly, what happens when you run a single step of the model on these varyingly partially noised images, right? So what this running a single step of the model on these images gives us is, if you are 25% of the way through the diffusion process, what does it look like when you undo that, right? And similarly for each of the percentages here. So then you just show the images, and this is what results. So when you're 5% through and you undo that 5% of the noise addition, you get a fairly good image. When it's 95%, you kind of struggle. Or when it's 75, 65, you struggle. 91, obviously, right? But low percentages, you are able to extract out the noise pretty well. Even up to 0.47, you can kind of clearly see the underlying stuff, the underlying fashion and mist image. So then you go through the sampling, you do the BS of 2048, and keep in mind that we are now using the DDIM step. And if you don't recall that, go back and look at the DDIM notebook, which is the notebook prior that we had run, which is the denoising diffusion implicit models, where this whole concept of eta, and then utilizing or jumping through multiple steps that he illustrated. So those are some things to keep in mind. So DDIM step, you do that's where the eta comes into play. You do the DDIM step, and you use the DDIM version instead of the DDPM version to do the sampling. So here, the only difference is instead of using a range in order to get the steps, remember we did the 0 to 1,000 steps. So we say a range and then take steps in the inverse direction. That is, we go from 1,000 down to 0 in order to get back the clean image. But now instead of doing that, because this is a cosine function, it's kind of a smooth function, right? It's smooth continuous values between 0 and 1. So we can now use a linspace in order to go, the similar concept of steps exists, but it's a continuous smooth value of t's that we extract. And then the rest of it remains the same. Calculate the A bar, and A bar now is a calculation rather than a lookup table kind of approach. And then you do the noising, and then we do the next A bar, which is whatever current step is minus 1 over step. So if you're doing 1,000 steps, it would be current minus 0.001 because it's a continuous value, if you recall. And so we just step through that linearly. That's for A bar T1, that is A bar minus, you can think of it as the next step. And then you get the x0 hat and x of t from this, and you kind of return the parets to which you have just appended the predicted x0. So if we just did the DDIM for 100 steps, then he says, now we get a FID of 3, which is actually quite a bit better than what we got previously in the prior notebook. And if you go through the process, as I told you, we do get a FID of 3. So this way, if you run this notebook, this is true enough. We still, even with all the diffuse change and everything, we still continue to get a good FID score of 3.38. Now, the actual FID of a batch is somewhere in the 1 point something range. So this is getting pretty darn good with respect to reproducing our or generating our original image. So you do the threads and you compare it, you get a 3.96. If you do a steps of 100, but with an ETA of 1.0. And then you do 50 steps instead of the 100 steps. So this is one where, you're jumping steps, you're taking less number of steps than 100, and it doesn't quite double, but you can see the FID has increased. So when you sample less frequently, then obviously you don't get as good image, as good a set of generated images. Of course, you could plot this visually. I don't know that you'd be able to tell the difference between 4 and 6.6, but nevertheless, these are pretty good scores. And obviously you would get a 2x, at least a 2x speed up when you sample less. So this is just an illustration that cosine scheduling does get you, combined with DDIM sampling, does get you a reasonably good set of FID scores. And these images are pretty darn good compared to the original reference images. So that's what the cosine schedule notebook is about. And as I mentioned, this notebook does work even with the set of issues that you'll face. But if you include import K-diffusion, and another trivia that I had to spend a little bit of time figuring out until I stared at it long enough to realize it's frustrating why they do this or why this is done this way. But K-diffusion, if you look at K-diffusion here, the pip install is K-diffusion. So you have to install K-diffusion, which is the installation, but the actual utilization of K-diffusion is K_diffusion as K. And so I was originally importing K_diffusion, and it kept giving me error until I figured out why. And it turns out that what you actually import is K-diffusion, and you use K_diffusion. So another thing to keep detail, little slip-ups that you need to keep in mind. As I said, you also have to install transformers before getting into mini AI installation. Otherwise, your unit import, which you do when you try to import unit, which you do here, the unit TD model, that will give you an error if you don't have the transformers imported right now. And strangely enough, it's just because of some Python, type hint that uses something from transformers, which is really weird. But nevertheless, that problem is sidestepped by importing transformers. Okay, now having gone through all that, the next notebook, which is the one that didn't work at all for me, and it works, but it doesn't do what Jeremy says it is supposed to do, or at least he illustrates that it works for him, but it doesn't work in what I tried, and I didn't try to debug it yet. I might do that over the next week. So in this notebook, what Jeremy is trying to illustrate, and it's somewhat off the beaten path because it's not relevant to our understanding of the way the algorithms work or what he will get to in the next implementation, where he tries to continue to kind of improve our understanding of the stable diffusion algorithm. But in this case, the fundamental idea that he is after, and he kind of wants to illustrate the nature of the research that he does along with his the people who are assisting him with this particular set of lessons. And the goal overall of this notebook is to kind of illustrate, can we get rid of providing the noise along with the time step, or I should say providing the time step along with the noised image in order for the stable diffusion algorithm to perform well. And Jeremy's idea has always been that a neural network which is predicting noise should be pretty good in terms of its ability to predict the noise. So why do we provide it with two things which are noise related? One is the noise image. If we just give it the noise image, it ought to be able to predict what the noise is in the image if we have trained it to do that. But what we actually do in stable diffusion, as we have seen so far, is not only provide the, especially during sampling, not only provide the noise image, but also provide the time step corresponding to which we have added noise. And you can think of it as time steps, or you can think of it as a continuous function. It doesn't matter. What we do provide is an additional input corresponding to either the fraction of noise we have added or the time step corresponding to which we have added the noise. That's provided in addition to the noise image. So we send in an XT, and we also send in a T or a proxy for T. And his idea in the notebook is, well, I don't think that providing this additional T input is really necessary. And he wants to see through research whether his idea holds up. Are we able to do the stable diffusion process without providing this additional input? So that's what this notebook is all about, just to lay the context. So all the initial imports and stuff. And as I said, the goal is to predict the noise level so it can be passed into a pre-trained diffusion model. Right? So all this is the same. Now we are using 28 by 28 images, and what we're going to do is not going to predict noise given the noise image and T. Instead, create a model which predicts the T given the noise image, which predicts either the time step or corresponding to the time step, the noise that's there in the image. So his point is, when you look at a plot of images with noise, it's obvious roughly how much noise each image has. We saw that even in the prior notebook where I showed you the various amounts of noise added. So he says, wait, if we can see that there's less noise here, and we can see there's tremendous amount of noise here, and there's kind of intermediate levels of noise here, why can't a network detect this without us also providing this, 0.05, 0.25? No, just send in this image and expect it to predict the label corresponding to how much noise there is in the image. And can it do that or not? And do we need this additional T input when we do the denoising or when we do the prediction? So that's the question. Why do this, which is passing the amount of noise, since the model can figure out how much noise there is, right? Can that be obvious to the model? So create a model to figure out how much noise there is when you just have the noise image. So that's what we do. So now we change the noisify in this case. So if this one grabs an alpha bar t randomly, it's a random number between 0 and 1. So it's this smooth continuous concept that we use here. Grab one value for batch, then we noisify. And in this case, our independent variable, therefore, is the noise image. And the dependent variable that we are asking the network to predict is the alpha bar t. And alpha bar t, as you can see, as you can recall, is just an equation to get to the t value. So once you have alpha bar t, we can get the t value. That means we can say what is the amount of noise or what's the fraction that we are through in terms of adding noise. So we create a model that predicts the alpha bar t given a noise image. So alpha bar t goes between 0 and 1. So typically, you might consider putting, this is an interesting detail. He says that ultimately what we are predicting is a value that goes between 0 and 1. So typically when we do that, then the way to predict something which goes between 0 and 1 is to have a sigmoid at the very end, right? So you just collapse all values and make it go between 0 and 1. But what he found is that for two reasons, he doesn't do that. One is he says that the difference between, he wants the ratios to be important. And then the other is more of an empirical reason, that if he does logit, then he finds that this network that he set up actually works and does something useful. But when he doesn't do the logits and instead does the sigmoid, it doesn't work. So he kind of goes into, in the lecture, excuse me, that these kinds of details are important and we need to kind of play with it to see, does it work when we use logits or does it work when we use sigmoid and so on and so forth. He doesn't get into an explanation of why one would work versus the other doesn't. But this fact that he extracts the alpha bar t and then takes the logits is the reason that he claims that this begins to work. But as you will see, it fails miserably, at least with the current implementation, as we'll see as we go through the rest of the notebook. The rest of it is identical. You do the same things as before. And here, obviously, the noise is added, and then you have these values. So, the different fractional values. Now, one of the things that you get into a difficulty when you do this is what counts as good. That is, if we just predicted, obviously we are predicting alpha bar t, but what is kind of a reference prediction to which we can compare to say, oh, we are better than guess or average guess. And so in order to do that, he said, what if we always predicted a constant? So he uses a 0.5. Now we can change it to a 0 if you want and check. But bottom line, he just says, what's a baseline naive model which just predicts a constant value? And he defines a network which just predicts a constant value, defines a matrix which is just a standard, nothing but a matrix callback. He finds the loss by passing in a batch through and by fitting for one batch, and the loss he figures out is 3.5. So the whole exercise is basically to say, if we did a naive prediction, which is a prediction of a constant 0, regardless of what we get as inputs, then what's the MSE loss? And by calculating the MSE loss, we found it's about 3.5. So if you're getting somewhere around 3 in terms of loss, then our model is not learning anything. because it's as good as just predicting a constant value all the time. If on the other hand we're getting a value much smaller than 3, then our model is learning something. So this is an attempt to answer the question, how do we know whether our model is learning anything in this process? So he just says, you flatten it in order to compare two values which have different sizes, but the model is the same now, but this is a regression model. And so we kind of have a single output, right? Instead of because we are predicting alpha bar t, which is the fraction or the percentage or, floating point value. So it's a single value. So that's the one difference. Instead of classification into 10 different values, it's a single number that we're trying to predict. So that's the only change in the model. Use the MSE laws, everything else is the same. He fits and does the model, samples it using see how it's doing by grabbing one batch of noise images, putting through our model, and then kind of using our model to predict what it looks like. And here it seems to be doing something good, or at least seems to be predicting something close enough, but it's not already close enough. I've seen this before I started using the latest diffusion model. If you compare, this model, for example, says that this particular shoe has a value of 0.89 in terms of alpha bar t, right? Now, that's what it predicts. The actual shows it's 0.95. Now, the interesting thing for me is when I was running this notebook before I used the latest diffusion model, this gap between what it predicted and the actual was at most in the second decimal digit. So if this was 0.95, it would predict something like 0.94, or sometimes it would even predict exactly 0.95. But what you see now is most of these predictions are off by quite a bit. So for example, you see this 0.36, it predicts as 0.25. You see the 0.65, it predicts as 0.72. This 0.91, it predicts as 0.81. I did not see as much gap as this. There was just a gap in the second decimal digit when I was running this earlier, just a week ago. So something definitely has changed. Now, obviously, we have not, in this notebook hasn't changed. So I think something underlying has changed. I haven't bothered to chase down what are all the changes that have happened. Also, this figure where we end up is much higher. And you see, even in the training, I don't know whether it's a plot. Oh, yeah, there is a plot. So you see this spike that happens in the training loss. That's something which I'm seeing consistently. This did not used to happen previously. And in fact, while I was playing with this notebook, I trained it twice. And then in the second time when I trained it, then this went away, the spike. So I don't know what's going on or what are the reasons for this behavior, but you can see the spike is because after training for about 5 epochs, you see this sudden spike in the value. I don't know why that happens. But again, after that, it keeps going down. It ends up at 0.6, but you can see that it actually started at a loss of 0.3. So something weird for sure is happening, and he ends up with a loss of 0.075, which you can go and look up in his reference notebook, but that's definitely what I'm getting as I run this. So right there is an indication that we are somewhat off the rails. And also, as I said, if you compare what it predicts to here, his predictions are much closer than what this network is doing. So somehow this network is unable to learn well what he wants to learn. That is, when you're passing in without the noise, it doesn't learn well. But in his case, he goes through, he tries to do so then he kind of actually trains the model using a cosine scheduler, noisify. The unit model obviously is expecting two values, which is the t value as well. But in this case, we don't provide it any t, so we just provide it a constant 0. Right? And then initialize in the same way, train for 25 epochs. The second training, in fact, again, works fairly well. Funnily enough, I end up with exactly the same loss value that he talks about. But when I go to sample and use the appropriate pickle, and then load this data aug to pickle, and then do the deeding step as per normal, and I'll get to why there are so many different deeding steps. Let's just assume we use the last deeding steps here, and then do the sampling as usual. But again, in the sampling, when the model is called, we have no t to pass in. So we just pass in the xt, right? Which means we don't pass in the time step, we just pass in the noise image, because that's the whole purpose of this research notebook to do. So, so the point is he still knows the t, because when you do the IT in enumerate progress bar time steps, you still know where you are on the time steps, but you just don't pass it to the model, because the model only takes the noise image. That's the single xt that's passed to the model. Of course, the unit model, we just pass in the noise of 0. But as the second value, because model is set up to expect two values. And then we get the x0 hat, we do the set predicts, and his value that he finds is a FID of 22. And look at my FID, it's 1708. So that's what I meant by saying something is broken, because obviously FID of 1780 is meaningless, or at least it tells us that something is very wrong. His experiment, he still considers the experiment a failure, which I would agree with, given that the FID is 22, whereas you saw that by the time we ended up with a cosine schedule, we were able to get a good FID of about, I don't know, 3 point something, 3.8, 3.7, and so on. So FID of 22 is obviously far worse. So he said, oh, my experiment to try to generate the same results while not providing t failed, but let's play with it some more. Let's not give up, and let's see whether we can improve the FID. Now, obviously, in our case, the FID is way, way off the chart. So our rest of the notebook continues to fail. It generates numbers that are closer in the FID numbers, which are closer to in the thousands. But anyway, play with it yourself and see whether you can figure out what is going wrong compared to what Jeremy has done. But I think it's nothing in the notebook that we have done improper or incorrectly when using and executing the same code. Somehow the underlying diffusion model has changed, which is causing the problem. But it was still an interesting challenge to debug as to why and what are the causes. But so here, what he says is, okay, we are not passing in the time step, but one of the things which is interesting when we don't do that is the amount of noise removed, the amount of noise that the model has to remove is obviously dependent on the time step. When you have a time step which is much in the forward process, which is much farther along, then you need to remove a tremendous amount of noise. But early in the process, again, forward process I'm talking about, you have to remove less amount of noise, right? Because the amount of noise you've added as you noisify is less early on. So for example, when it's 0.05, then it's only 5% of the way through the forward process, so less noise. When you're 79% of the way through, then you're obviously adding much more noise. So the model doesn't know this exactly. So it may remove a little more or a little less of the noise. That's the reason that he says that there is some slight difference between these two sets of images. That when it says, and again, I keep repeating, but it's important to keep in mind that in his pictures, if you go back and look at his notebook, the delta between what it predicts and what it has as the actual is much less than what I see here. So already our network is performing far worse. And I think that has something to do with the instability in the training and stuff. But because of that, his point is, even in his case, when the numbers are closer, they're not perfect match. They're perfect match in some cases, but they're still off by the second decimal digit. Obviously, in my current notebook that I'm showing you, these numbers are way off. It's 0.95 versus 0.89 and 0.81 versus 0.91. But in his case, they are a lot closer, but closer, not exact. So what he says is the model may remove little or more noise than what is anticipated to be perfectly removed or to be perfectly aligned with what amount of noise has been added. So sometimes it's going to not remove the whole noise or all of the noise, for example. So he changes the de-dim step through which we sample, right? And that is the reason. So this is the original de-dim we use here, and we pass in the de-dim step as F when we sample. So this F is this, the F that's passed into sample is this de-dim step, okay? But now he says, let me try and make or modify the de-dim step, and the modified de-dim step are these two. And I think this is just him playing for these two codes. He just kind of printed some values and stuff, and he left it in just to show that when you're doing research, things don't work the very first time you try. You have to play with it and figure out, print, whatever. So, but his point is he changes the de-dim step, and the way he changes it is he kind of, this particular value sig is the same as before. These two lines, this is the same sig step as what it is here, but he kind of does something different in the de-dim step. Instead of directly calculating the x0 hat from alpha bar t, he uses the model that is the same model that we have trained here to predict, use the t model below, right? And then, which is this t model, passing the noise image to the t model or the alpha bar model to get the alpha bar. Now, again, notice here is using the sigmoid to predict the alpha bar between the values of 0 and 1. And then for each image, this way, we ensure that we are using the predicted alpha bar, right? And in order for this alpha bar to be not crazy, he kind of finds the medians of the alpha bar and then he clamps the alpha bar value. So this modification to the de-dim, he thinks will improve, right? So rather than just using a calculated alpha bar t, use the estimated alpha bar t for each image and clamp to be within certain values of the median. Now, this is where, why do we, or, why did he think of this as an idea to improve? Don't know, but at least what he in his notebook illustrates is once we use the model to predict the alpha bar t, clamp the alpha bar t value so that the model is updating it based on the amount of noise that actually seems to be left behind rather than the assumed amount of noise that should be left behind. So it's kind of, he's trying to eliminate the difference between these two values, if you will, like don't make assumption, kind of predict and use that value of alpha bar t, and using that and clamping that value to be within some range of the median, his numbers, he says, improve quite a bit. So using the new de-dim step, which is this guy, which I try to do. Then he kind of, with that step made to dig in, we see the results below, but as you see, I don't see anything but noise. So obviously some problem, right? And his FID is a lot better. So he gets a FID which is fairly close to the FID that he was getting before. Also, and we have seen this before, when he plots the KID or the FID, you should see it go down right, over time, because obviously the FID has to go down as you go through the steps towards zero and you get the clean image. You start with the noised image and you get the clean image. On the other hand, you see what happens to KID in our case. It kind of does the exact opposite. Here the KID is increasing as we denoise the image. So something fundamentally seems broken in this notebook compared to, and then he does the, he evaluates the FID under a variety of conditions. And he does that by repeatedly executing cells back and forth. I hate that because then I can't correlate what happens, where the results are produced and what is the outcome of what run. So I unrolled the notebook and ran it, but regardless of what I do, you can see that the FID improves a little bit, but this is still garbage compared to what we are aiming for. So it's in the thousands. So anyway, I would encourage you guys to play with it as well. And let me know if you're able to get much better FIDs, and if so, why, and what's changed or what you see as being problem with this notebook or with the underlying diffusion model, or what you observe as you run this one. Any questions or comments or thoughts?
I had a problem where those numbers, that accuracy numbers, were being converted to NaN. Those loss numbers were being converted to NaNs. So the model.
Yeah, if you rerun it, sometimes that doesn't happen, but it happened to me as well. And I reran the notebook and it worked. So I think that's also indication of the underlying instability of training this model.
Yes,
I did encounter that.
And then I tried using lowering the LR rates from 1 e-neg 3 or 4 e-neg 3. I got to 1 e-neg 2, and it worked. So I have been tinkering with the LR rate here. Maybe if you try tinkering with the LR rate,
no, but
those
the question
spikes
is,
won't.
did you get any? But the question is, did you get any results that were as good as what he claims?
No, I didn't get the results that were any good. And those were quietly blown away. Those FID scores were quite high for my on my end. So
yeah. But again, as I said, this is more of a research direction that he was trying, saying, oh, I just think that providing the noise and or the time step and the noise image is not necessary. But actually all modern, he himself admits that, at least as of, I haven't looked at research papers in the last several months, but as of when he was teaching the end of this course, which I believe was earlier this year, January, February of this year, the state of the art was still using not just a noise image, but a noise image and time step value provided as input, or fraction or some indication of the amount of noise in the image along with the noise image. So that's kind of a detour and an indication of how he does research and so on and so forth. Not really material to our understanding, but it kind of gives an insight and something else for us to play with and figure out why this doesn't work. But from there, we move on to now to a set of two papers, one that he just refers to and discusses in theory, and then another that he actually implements. So first, let's look at the paper that he refers to, which we will discuss, and I'll share that. I'll show you folks the paper. When you can see it. Yeah, so this is the paper that we'll discuss a little bit, at least in theory. So this is a paper by some Google Brain team. And as you can see, we tried two schedules, right? One is the linear schedule in the forward process, and then this cosine schedule. So this paper discusses the importance of noise schedule for diffusion models. Bang on, right, what we have been kind of playing with. So this is an important element. Scheduling or noise scheduling is an important contributing factor to how good our generated images on diffusion models are. So that's kind of the takeaway. And the key takeaway from this paper, and you can see some of the images that are generated are just brilliant and beautiful, very clear, and they are of different sizes and different resolution and stuff. So he then begins. I'll share the discussion of this paper, and then we'll go on to implement actually a similar paper, but from NVIDIA, that really thoroughly explores the design space of all of the contributing factors to get good generative diffusion models. But first, let's kind of go through this paper. So what the paper talks about is the strategies for noise scheduling for diffusion models. So three key takeaways from the paper. One, which is the type of schedule we use is crucial for performance. Also, there is no single schedule, like there's no, cosine scheduling is the best or linear scheduling is the best. It kind of depends on the task. So that itself is interesting, right? There's no universal best schedule. Second, that when you increase the image size, then, and you can look at the details in the paper, but when you increase the size, when you go from, a fashion MNIST, which is 28 by 28 to 32 by 32 versus you use 256 by 256 or 512 by 512 or even 1024 by 1024, the type of noise schedule you want to use changes. Right? Secondly, or thirdly, scaling the input data by some factor is a good strategy for dealing with differently noised or different sized images. Now, this is exactly the problem that Jeremy saw, and he was just randomly, empirically changing values, right? Like he had a bug which put his image values in 0 to 1, changed it to say consistent with all images, so -1 to 1. So all of his results go to the dogs. And he said, wait a minute, if a bug actually makes it better, what the hell is wrong? Figured out that, maybe it's the range. Maybe we don't want the range to be wide, like in -1 to 1, which means a range of 2, versus a 0 to 1, buggy, but still in a range of 1. So he kind of chose to recenter it, to center it at 0, but maintain a range of 1, right? He kind of stumbled into it empirically. But what this paper shows is that if you want to get good results, besides scheduling, the range is important as well. So it kind of confirms what he empirically stumbled onto by trying to fix a bug and trying to get the diffusion process to work well. So the paper actually discusses, do we scale or do we, normalize, or what do we do? And so scaling the input data is, besides using a good scheduler, are two different important contributing factors to how good we can use a model for generating diffuse or for generating good images from diffusion models, right? And then they demonstrate the effectiveness of the method by training a very high resolution model on ImageNet. And this is a class conditional model. So far, what we have been working with is obviously there's no class conditioning, which is to say we just generate randomly any one of the 10 classes of fashion image. We don't say, oh, I want a conditional, I want you to generate an image which is a shoe. So that's not what we are doing yet. We'll kind of look at how to do that in a subsequent class. So he walks through the paper. The paper, again, unfortunately, uses yet another terminology. It uses gamma, which is for the continuous time case. So instead of alpha bar and beta bar scheduled for 1,000 time steps, there's some function gamma of t that tells us what alpha bar should be. And it takes in a time step from 0 to 1 and used to noisify the image. But again, identical concept, just the terminology used is different. And so what it paper seems to show is if you have a small image, then adding a lot of noise is not a good idea. And if you think about it, it kind of makes sense why this is the case. Because if you have a large image, like a 512 by 512 or a 1024 by 1024 image, then when you're adding noise, then the noise tends to be distributed across the entire height and width of the image, right? So whereas in a tight 32 by 32 or 64 by 64 pixel images, then adjacent pixels, because it's very tiny, and so adjacent pixels may not have much in common. So when you add noise, you're kind of displacing the pixels much more as compared to adding the same amount of noise in a much larger image. And that kind of intuitively makes sense. So when you add the same noise for much bigger images, then the noise averages out, which tends to still leave a lot of the original image back in the image. So adding the same amount of noise doesn't work in small images versus large images. So that is something where the size of the image matters. This is the reason that the scheduling of noise for small versus large images matters. So the same noise level for different size images can make the task of the diffusion model harder or easier, right? And we'll see the picture. I don't want to keep switching between PDF and here, but we'll see that in a minute when I switch back to the PDF file of the paper. So you use different noise schedule functions, the original version, which is the media schedule, then there's the cosine schedule, and then there is a sigmoid-based schedule. We can see that, I believe, although I'm not 100% sure of this. Then they show the continuous time variance of these different schedule and how you can change various parameters to get different gamma functions. Remember, gamma function is just equivalent to an alpha bar t function. And remember, we always go in the forward process from clean image at T0 to all noise at T1. So the path that's taken from T0 to T1 is going to be different for these different functions and parameters. And the important thing they kind of zero in on is the signal to noise ratio in the image, or the log signal to noise ratio. And that changes over the different time steps that we take. So if the diffusion model is not training well, then the things to change or play with is the noise scheduling. Then the other thing is we can change, obviously, the classes of noise scheduler, and you can go from, or you can also change the parameters in one class of noise schedule or switch from a linear to a cosine to a sigmoid. And again, I'll kind of show the pictures from the PDF that refer to this particular slide. The second strategy by which we can improve the learning of the diffusion model is by the scale. And this is where the scale is the important thing we kind of stumbled on, or Jeremy stumbled on in his lectures, but they have kind of identified it through rigorous experimentation. So, and that is adding some scaling factor to the clean image. Interestingly, we just stumbled on using a value of 0.5, right? That's why the range of 1, which is from -0.5 to 0.5. But he was just trying to get better results. He didn't kind of theoretically or know that there was a theory behind it as to why diffusion models learn better when the range is played with. So keeping the noise schedule fixed, we can scale X0. And which is why does it help? Because it changes the noise signal to noise ratio. So for different amount of scaling, you gain different signal to noise ratio. So that's the reason why the diffusion model learns better, right? So this kind of gives us the theory behind the empirical things that we observed. And of course, you could have a combined strategy, which is what they eventually implement in the paper, that combines scheduling with scaling, right? And then they conduct a whole bunch of experiments and report it in tables. So they come up with best schedules for 64 by 64 images, 128 by 128. But the interesting result they report is they're not the same. So there's no single best scheduler. It kind of depends on the data and the size. And it's the same thing for scaling. At different sizes, with whatever schedule, different values are shown to be optimal. So the takeaway is scheduling as well as scaling are key. And then they come up with a rule of thumb of how to scale the image based on image size. And they also use something which I haven't looked into yet, which is called a recurrent interface network. Jono, who is the co-lecturer in this course, says that that's a very interesting paper. I'd like to read it, but I haven't yet. But they seem to get some advantage from using the recurrent interface network. Obviously, we use just ResNet, but and they get these cool results that you saw on a very high resolution 512 by 512 124 with 120, right? And then he also talked about how well we train, how many steps we take in inference, and can we take, for example, 1/3 of the steps that others do? And if you recall, this was something that towards the end of last lecture we played with, or Jemmy played with, where he takes less steps in the beginning as we denoise. So as we are going from xt to x0, then he takes less steps in the beginning because there's a lot of noise, and takes many more steps as we get closer to a clean image, right? So this is where the leading step and 100 or 50 or 20, and do we continue to get a FID, which is as good as the reference FID that we got. Those are the things that we can play with. And they say, oh, can we get a much faster sampling process while maintaining the quality? And what do we do for that? So besides scheduling, scaling, they showed this recurrent interface network is important, and then they kind of discuss how best to do the sampling. Then we discuss in the next notebook a paper from NVIDIA, which looks at this entire design space and does a very thorough analysis and comes up with a new set of parameters that really improves the overall process. And we look at explicitly at the input scaling. And in this case, when we implement the Keras paper, we'll see that we are actually choosing to go in the range between -1 to 1. There's no accidental bugs that we are debugging and so on. But before we go to the Keras paper implementation, let's look at, because I just kind of talked about it, but I can show you some of the results. Let me share my screen again with the PDF. Let me know when you can see it.
We can see it.
So here's the gamma value that they introduced in the paper. And again, it's just like alpha bar. You can kind of see that they are adding the square root of what we've done with alpha bar, some clean image, and some amount of noise. And here's the thing I was rambling on about the amount of noise added. It's kind of, you can see when it's 64 by 64 how noisy it is when you have the same noise. But when you go to 512 by 512, because this amount of noise is averaged out across this entire large image, you can see that it doesn't seem as noisy. So that's the first point that the slides made, right? The second thing is we talked about these curves. Like this is the cosine-based scheduling. This is the log of the signal to noise ratio. This is sigmoid based, and then the log of the signal to noise ratio. But it kind of shows you that there is different kind of parameter values of a cosine based schedule, and by playing with the parameters, you get differently shaped curves. They in turn add different signal to noise ratio to the image, and that's kind of what I referred to in one of the slides, right? And then there's this whole B, which scales the XZO. This is the scaling factor. So this is just scaling the input. This is the -1 to 1 or -0.5 to 0.5 or 0 to 1 or whatever. So that also has an important impact on the result. And then they put it together and show a simple compound scheduling strategy. This is not something that he implements, but it could be an interesting exercise for us to play with. But what he points to, which is interesting, is that depending on the noise scheduling function, here is sigmoid, here is cosine, you get different values for the best scheduling function, which gives the best results. For a 64 by 64 and a noise scheduling function of 1 minus t, it's this particular, for 64 by 64, you get the best result when you use this scheduler. But you use this sigmoid scheduling with these parameters, for 64 by 64, you get 2.03. But for 56 by 256, again, the parameters have to be played with. For 128 by 128, it's different set of parameters. So you can see that there's no single scheduler that gives you the best result independent of size. It depends on the size, what kind of results you get. And they're kind of showing you that it's the same thing with the scale factor. You get like different scale factor for different size of images that you get the best. And then they implement it with the whatever recurrent interface network and show blah, blah, blah. But this is not so important for us. What is important is we've shown that, or this paper has shown that, a couple of things we have been playing with, which is scheduling of noise as well as the scaling. Both are very important to get the best. Okay, with that discussed, let's now move to the last paper that he implements in this last notebook that will be discussed today. Okay, I think you should be able to see it. So the Karras paper, as he refers to, is what we will consider as the last paper for today's discussion that he implements. So here in this Karras et al. From, let me tell you the actual name of the paper. It's called Elucidating the Design Space of Diffusion-Based Generative Models. So that's the name of the paper, and it's by Tero Karras from NVIDIA and a bunch of people, all from NVIDIA. So that's kind of the paper we are discussing and its implementation. So what's different about the paper and what they are doing in the implementation here? Again, same thing, you have to install K-diffusion, and you have to also do the transformer thingy. Rest of it is the same. And now we are explicitly choosing the range to be between -1 and 1. And again, there's some, this is an interesting thing. If you're attending a live course where Jimmy is also conducting research, you get exposed to some of these. He originally, when he refers to in the lecture, says that he calculates the XB or the standard deviation for a batch of data, but he did that with a -0.5 here. And so he claims that his original SIG data was 0.33. and he got good results with that. But as you can see in the notebook, by the time the notebook was published, the final version of the notebook that was published, it was published with 0.66. So you can kind of ignore what he says in the video. Currently, at least, he's using the correct, proper standard deviation. Okay, so the interesting thing about this paper is the following idea, that how do we make a network that really is challenged equally at both ends of the spectrum? What do I mean by that? Well, the idea, if you think about it, is that, the paper talks about is sometimes, remember, so far all we did in the network or the networks we trained always predicted the noise. They are noise prediction networks. That's the theory, or the, on which, that's the foundational theory on which the entire diffusion models for images is built. But the point that the Karras paper makes is sometimes just predicting the noise is a bad idea. Why is that? Well, the idea that's proposed in the paper is predict noise sometimes, but sometimes predict the image. Now, why does that make sense? If you think about it, if you are predicting noise when you are at the end of the forward process, when most of your image is noise, then the model doesn't have a challenging problem to solve. You can just predict all noise as you get closer, and that would be good enough, right? The model would do well if beyond, to oversimplify, beyond the 50% point, if it just keeps predicting increasing amount of noise, the model would do fine. That is not what we want. What we want is for the model to actually learn even as we go towards the end of the forward process. So the point is that if you're given all noise and then ask the model to predict something, then predicting noise is wasteful because the model is not learning much. Similarly, if you are very close to the initial steps in the diffusion forward process, then you've added very little noise. So at that time, again, if you ask it to predict, then that's also wasteful. So the point the Karras paper makes is you want an equally difficult problem to solve, regardless of whether the image is noisy or the image is clean. So what you want then is the model to predict sometimes an image and sometimes the noise, depending on which is the more challenging problem to solve. Because that way you'll ensure that the model is learning something valuable. Because if you, again, keep in mind that if you're predicting noise when most of what you are adding is noise, wasteful. If you're very close and you're adding very small amount of noise, then again, that's not very valuable thing for the model to predict noise, because noise is so less, there's not much that the model is learning. So the idea that the Karras paper comes up with is to say, let's have the model learn and predict different things depending on where it is in the diffusion process. So how do you do that? And they come up with this number that's called C-skip. It's essentially a number, and rather than predict the noise or the clean image as the target, so the target thus far has always been noise, right? It's the noise, that's the noise prediction model that we are building. But now what we are going to do is build a model which predicts noise or predicts image, depending on where we are in the diffusion process, because that way the model learns more and it's a better model. So what we try to do now is the model is made to predict a LERPed, and by the way, for us, since we have been following the course, a LERPed version basically means that it's one of these exponentially weighted average moving averages, right? So that's what LERPing is. So you predict a LERPed version of noise or a clean image, depending on how noisy it is, right? So in this equation, which is taken from the paper, the things to orient ourselves with is Y is the clean image, N is the noise. Okay, again, Y is the clean image, N is the noise. So Y plus N is the noised image. So now we have added this skipped value, C skip value, which is just a number. So C skip of this row, and we'll learn a little bit later how we choose this value. But let's focus on C skip and Y plus N. Again, to repeat, Y is the clean image, N is the noise. So this is a noisy image. This is the clean image. So if C skip were to be 1, then let's go through this equation. Because if this is 1, and this is Y plus N, this is Y. So when you subtract it, you get the Y minus Y plus N, and this is negative here, so N. So that means when C skip is 1, this is essentially just the noise, right? So when C skip is 1, we predict noise. On the other hand, let's assume C skip is 0. When this is 0, this entire thing is gone. So what we are predicting is Y. That means we are predicting the clean image when C skip is 0. We are predicting the noise when C skip is 1. So by introducing C skip, we are able to modulate what the model predicts. If it the noise, then its C skip is 1. If C skip is 0, it predicts the clean image, right? So by modulating the value of C skip between 0 and 1, in one case we are able to make the model predict noise. In the other case, we are able to make the model predict the clean image, right? Now they make C skip a function of the sigma. I call it rho. It's actually sigma. And I was guessing, again, this is more of a guess on my part, but maybe sigma actually indicates the signal optimization. I don't know that for sure. But the bottom line is we do not any longer have alpha bar, beta bar, and so on. We just have sigma. It's kind of unfortunate. It's yet another variation we saw when we went from DDPM to DDIM. DDPM used, alpha bar, blah, blah, blah. And then DDIM came along and used alpha, but that alpha in turn referred to alpha bar of the original paper. Similarly, this paper is using sigma. Sigma is unfortunately used already in DDPM and DDIM. And again, yet another variation. The sigma here is equivalent to our original alpha bar. Very confusing in terms of its terminology, but nevertheless, the bottom line in this paper is sigma. Sigma is equivalent in concept to our original alpha bar, but they introduced this new value C skip, which helps us determine, are we predicting noise or are we predicting the clean image, right? So this is what it is. It predicts the noise or predicts the image or something between the two values. Now we'll skip through this scaling. We'll come back to it in the future, but let's look at the chart, which is kind of showing the loss of a trained model. So here we are plotting. Now, how do we choose? We know what values we want C skip to be, but C skip is a function of sigma. And here is a plot of sigma and loss. So what we find with this plot, or what they determine with this plot, is when sigma is low, as it is here, or sigma is very high, as it is in this region, right? Very low. See, when sigma is low, and sigma is alpha bar, so very small alpha bar, or when sigma bar, so just orienting ourselves, sigma is very low here, that means alpha bar is low. Sigma is very high here, that means alpha bar is high. Sigma is, or alpha bar is in the middle range in this somewhere here, right? Now, when it's nearly all noise, which means sigma is low, alpha bar is low, right? Or when it's nearly no noise, that means sigma is very high, alpha bar is very high, then we're not basically able to do anything. That's what this chart illustrates. We're only good at predicting when there is a medium amount of noise. So when we are deciding what sigmas we are going to send to this equation, we first need to figure out what's the range of sigmas we are going to send into this equation, which in turn will determine our C-skip, right? So what we do is we choose the values of sigma in this middle range that's from this red graph. But this middle range is basically along, it's just a normal distribution, right? Where the x-axis of sigma is a log curve. So this is just a log normal distribution or a log normal curve. So to get the sigmas that we want to use, just pick a normally distributed random number, which is what we do here, torch.rand of some 10,000 values. Then exp it, which means exponentiate it in order to get a log normal distribution. And then use a mean of negative 1.2 and a standard deviation of 1.2. I don't know exactly why 1.2, but that is the reason. The reason simply is that when we choose a mean and standard deviation of 1.2, it means that about a third of the time we get a number that is bigger than 0 from this signal sampling value. And the reason we choose this is if we get the value 0, then when we exponent it, e to the 0 is 1. So that means about a third of the time, the sigmas that we are going to pick are bigger than 1, right? Which means it lies here. And he just kind of plots the histogram of the above sigmas that we're going to be using. And the sigmas turn out most of the time to be less than 5. So it's less than this value here most of the time. But sometimes it's much bigger. And just a histogram plot doesn't show us that. So he kind of uses a KD plot, which says, oh, look at this. About 0.5 is when it dies, but there are a very, very small number of values that go even much higher. So Noisify, which is what we want to use to generate the noise, picks the sigma value that's using this log normal distribution. Then we get the noise as usual. And based on that, we calculate C-skip. So remember, we are going to find something between, or we are going to use C-skip to predict something between the clean image and pure noise, right? So that's, so what do we use for the C-skip value? The C-skip value is what is calculated in this scaling function, right? So here, the scaling function, what does it do? So once you pass in the signal, pass in the sigma value, then you do the total variation of the noise, which is sigma squared. So because sigma, then you just square it to get the total variation, but that's just the variation of the noise. But you also have variation in the data, which is, you know, the fashion MNIST or the ImageNet or so on, the data. And the variation in the data is data squared, right? So you combine the two and that you get the total variation. And the C-skip value, and we'll discuss later what C out and C in are, which is also the second and the third value that is sent out from the scaling equation. But for the purposes of, so C-skip is simply the ratio of the noise in the data, which is sig data squared, to the total variation. So if you just take the ratio of the noise in the data, the variation of data to the total variation, that's C-skip. That's what is used as C-skip based on our sigma value, which we choose from this log normal distribution curve through this sampling equation, right? And after doing all that, so we then get the noise, but now we calculate C-skip. So we are going to find something. We calculate it using the signal scaling function. We figure out the total amount of noise at some level of sigma, right? Which is what is the sigma squared. And then we add to it the sig data squared, which is the noise in the variation, is the data variation. And then we just add those two together and we take the ratio of that. And the calculator says, divide the variance by the total variance and use that for C. Now, why does this make sense? Does it align with what we were thinking of, which is if C-skip is 1, remember that in the equation, we were predicting full noise. If C-skip is 0, we were predicting clean image. Does that align with a choice of seascape? Let's think through this. If so, total variation is very large. That means it's very noisy. So the total variation is very large, right? Then seascape is going to be really small. So the second term in the Keras equation is very small, which is this guy. So if our noise is very high, this is going to be very low. If this is very low, it means this will be zero, closer to zero, which means we'll be predicting a clean image. So if the noise is high, then we predict a clean image, because that's a harder problem to solve. Because predicting noise, if the noise is high, is a less challenging problem to solve. Right? So we want to kind of make the problem equally challenging. Right? If on the other hand, if there is hardly any noise, that means our denominator is small, then the total variance will be really small. Right? So seascape will be very high. And if seascape is high, closer to 1, then we are going to be predicting the noise, right? As per this equation here. If seascape is high, this is because the total variation is very low. That means there is less noise. And if less noise, seascape is high. Seascape is high, this is close to 1. We predict all noise. Right? So we are kind of consistent with the choosing of seascape value based on the noise and aligning that with this equation and what we want the network to be predicting. So that's how we work. And then, so the target we are trying to predict is not the clean image, not the noise, but somewhere between the two, depending on where we are in the process, right? So now, the interesting thing though is using the seascape and Keras doesn't help us address the scaling issue. What it is helping us address is the lack of learning by the model, depending on where we are in the process issue. Because our model was cheating in a sense, or was not learning as much as it could by predicting noise when it's easy to predict noise. Instead, if it's easy to predict noise, we want the model to predict a clean image. If it's easy to predict a clean image, we want it to predict noise. So we wanted to face the harder challenge, regardless of where we are in the process, right? So, by the way, just here, another reference that he points out is sometimes this thing of using the seascape and so on is also called the V objective. So if you see some paper referring to V objective, and that's identical to the notion of seascape. That is the model predicting the harder thing to predict. And then the noise input is clean image. This is in terms of the, now let's look a little bit at Noisify. So Noisify, we obviously calculate sigma, which is exactly the equation that we showed before, and we calculate the noise, calculate the values using the scalings. We'll talk about Cout and Cin in a minute. We saw seascape come out of the scaling. Then we noisify the input, right, which is x0 plus noise times the sigma. Then we decide what our target is. And our target, as I have told you before, is now somewhere between a clean image and the noised input. The scaling applied to noised input, right? So that this is the noised input. We apply the scaling to the noised input. The noised input is x0 plus noise times sigma. We subtract the seascape times noise input from the clean image, and we divide by Cout, right? And so what we're doing is the scaling is applied to the noise input. So seascape is applied, the scaling is applied to the noise input, and then we scale the target up or down by using Cout. And we'll come to Cout in a minute, but a Cin is easier to discuss. So we'll discuss that in detail and then kind of imply that Cout uses a similar process. And in terms of what we are predicting or what we are returning, I should say, from Noisify, the scaling of the noise input by Cn, right? And then we just squeeze out the sigma and return the target of which is calculated this way. right? So the input to our model is scaled noise, which is this guy, scale noise. So you take the noise input and then scale it by Cn, sigma, just squeeze it to get rid of any excess dimensions, and then the target, which is somewhere between x0 and noise, right? So that's what we do here. Now, to understand Cn, let's look at the Cn equation. Either say, if you go back and look at the appendix of the paper, they talk about how the Cn and Cout, which are also come out of this scaling equation, how do we obtain these numbers? So what he points out is that actually what they do is fairly simple, at least as pertaining to Cn. So what they want to do is to say that we have this equation where we have y, which is the clean image, n, which is the noise that I've already talked about, and we want the inputs, which is the y plus n, the noise image, multiplied by this factor Cn, which is a function of sigma, the amount of noise we add. We want the variation of this entire thing to be equal to 1. Now, this is where Jeremy points out one thing. Throughout the entire course, he has been, repeatedly emphasizing a concept that we learn, or the networks learn better, and we spent a lot of time on this, when the mean is 0 and the standard deviation is 1. If we can keep that throughout the network, and especially also at the input, the network really does a good job of learning. We've seen this repeatedly. This is the reason we initialize the network in a particular way. This is the reason we use batch norms, so many other things, in order to continue to maintain almost at all layers the mean of 0 and a standard deviation of 1. So this is again something that they are just simply doing the same rule they are trying to implement, even as you go on to these more complicated processes such as diffusion models and so on. So if you start off with this assumption, then all you do is the variance of this is nothing but Cn of sigma is just a number, so that you square it to get the variance, and then the variance is just the variance of the noise image. But the variance of y plus n is just the y, which is the clean image, the variance in that, which is the square of the data, and then the noise, which is sigma square, because sigma is the noise that is the variance, is the standard deviation of the noise we are adding. So this is what it is. So now then, in order to find out Cn function of sigma squared, so Cn sigma is just the reciprocal of the square root of sigma square plus sigma delta square. And if this is the simple way by which they derive the value of Cn of sigma. And if you go back and look at the equation for Cn, because Cn is the last value we return, look at what that is. 1 divided by the total variance square root. And total variance is the variance of sigma. This is sigma squared, and this is sig data squared. So that's what is why Cn is this value. Because by choosing Cn to be that value, we are ensuring that the noise image standard deviation is exactly equal to 1. That's what we are trying to do. So, and similarly, by a similar extension, where the derivation is given here, we just find out what the value of Cout is, and Cout is this value, and that value implemented in an equation corresponds to this guy, sig times sig data by total variance square root. Right? And that's what this particular equation turns out to be, right? And those are the things we implement here. Everything else is exactly the same as before, nothing changes. And then some pictures of noised inputs with various sigmas. And remember, sigma is just alpha bar, right? So sigma with 0.06 is one with very little noise. Let's see, 0.06, no. So when I ran this now, we can look at 0.05. So when we look at this 0.05, this has very little noise, right? So if it has very little noise, in this case, the target is predict the noise, as that is the harder thing to do, because there's a lot of image. So it's the easier thing to predict. So you want the harder thing to predict, so you predict the noise. But when we go to an extreme like this is tremendous amount of noise. So the network can very easily just predict all noise. It will be easy to do. But instead, we force it to predict the image, which means it's going to struggle with that because this is mostly noise, right? So for something which is all noise, and again, the numbers may be different because they're running it multiple times, then you predict the image because that's the harder thing to do. For something in the middle, like 0.97 or 0.81, say, you predict some combination of image plus noise, right? To predict some of the noise and some of the image. So the reason for that is because our target is no longer just noise. Our target, as this says, is some combination of image and noise, right? So that's the noise input, we scale it, subtract it from the original image, and then we again scale that by the output scaling. So by doing that, then, and we print out the value of the noise input and stuff, and you notice that we get a value close to 1. That's the whole exercise. By doing the C in, C out, we have ensured that the variance or the standard deviation is close to 1, right, of the noise value. So the mean is not 0. Now here it says, hey, one of the things they didn't do, and maybe it's worth doing, is that if we make the mean 0, as well as the variation, as well as the standard deviation 1, then the network may learn even better. They didn't bother to do it, but maybe that's something we can work out as a enhancement to the process. So that's the basic idea of the Keras implementation. These values, C skip, C in, C out, why they matter, how is C skip related to the noise, and the concept of predicting or forcing the model to predict the harder thing to predict. Okay, and then we train the model in the usual way. And in this case, the model trains well. And then we can't obviously compare the loss because now obviously our model is and our target is very different. And then we begin to use, now we can grab denoise, or sorry, we can create denoise, which is similar to our inversion of the noisify. And that is just simply denoise the target and the noise input. We just reverse the equation, and then we begin to do the denoise process, grab our sigmas from our actual batch, calculate the C skip, C out, and C in, use the model to predict the target given the noise input and the sigmas, and then we denoise it. And these are the noise inputs we have already seen, and here are our predictions. And you can see that the predictions are pretty good. And here, unlike in the previous notebook, you can see the matching that happens, right? Like you can see 0.05, and you can see that 0.05 guy. You can see 0.19, you see the 0.19. So the predictions are pretty good, and you compare the predictions to what it ought to look like, and they look pretty close. Of course, there's something missing here compared to that, but still pretty close. So the sigma of 80, which is what they do when they sample full noise, they consider this pure noise level. Now, in the interest of time, I'm kind of going to jump through some things. You can listen to the video, but for full details. But if you here, he goes to various methods of sampling. Since we just have about 10 minutes, the sampling with this Keras approach becomes much simpler. In what sigmas to use for the reverse time steps. We have always used linear time steps, but this is where he begins to question kind of some of the choices that are made. And Keras runs, they analyze everything. So they run a bunch of experiments. They use different sigmas in case or different schedules. The sigmas they choose is based on this kind of a stepping process, which is described here. They use a value of rho, and they indicate in the paper that any value of rho greater than 5 gives you pretty much good results. And then they denoise it, and then they use different sampling methods. And he has discussed these. If not, you can go through the earlier notebooks. If you recall, sampling with Euler was the first method. Then there is the Euler ancestral, where you kind of store prior value, and these Euler ancestral, John, are all various methods to calculate the values using kind of a Newton-Raphson kind of technique, and with various approaches of sampling. And again, I kind of unrolled the notebook to make it simpler. He finds that some of the results that he gets are pretty good. Like, for example, here is the images, but this is with a Euler with 100 steps, and he gets a fit of 8. Now we saw a fit of about 3 in the best case with cosine, but again, given this is 8 compared to 15 is still pretty good. And then ancestral Euler, you get 8.5. You get ancestral Euler with, again, the eta value of 0.5. You're beginning to get close to the 3 we saw earlier, 5.35. The Hune, which uses multiple steps instead of each step, so you can kind of calculate multiple values there, and that gets you 8.16. With a churn of 0.5, you're kind of getting 9 or thereabouts. And then again, in this case, I didn't have time to debug. There's a linear multi-step coefficient, which is kind of one of the better ways of doing the extrapolation of the values we are seeking, which is different than the Hune method, because the Hune method runs the model twice. This guy here, the LMS method, tries not to do that, but obviously there is some problem with this particular line of code in the implementation where he tries to multiply the sigma max times the random values, because that doesn't run for me. But he says that with an LMS and with just 20 steps, we are at about 5.26. And for reference, the real batch of data passed through and fit calculated is about 1.27. So 5, 3, and so on are pretty darn good when we are doing the fit. So I kind of rushed through the end of this, but you can kind of go through the code and what it does and so on, and I'll post my commented code. So if you're interested, you can do that. So basically, here you take the average of the slope between 2 different points. So if you look at the Hune method, and for those of you who are familiar with the math of doing the derivatives and stuff, this is what the Hune method does. This is the point at which you take it, and this is the future point where you would have ended up. And so you take the slope here, and try to take the intervening slope. So that's what the Hune method does. So you then use this yellow line slope as compared to this guy or this guy. That's kind of the different sampling methods. But the interesting thing is you can kind of completely separate or orthogonalize the sampling from the way in which you have implemented the training process. The training process is where you use the scaling, C-step, C-skip, C in, C out, and kind of scaled it from -1 to 1, and then completely use variations in the sampling process. It could be Euler sampling with some some amount of noise added. If you recall, we kind of went in the once we took a derivative, we went all the way to the end, and then we added a little amount of noise coming back. And that is what is going to be used in the ancestral step. That is, how much do we go back in the existing direction and how much in the new direction, and that is determined by this data value that we pass in. So what we do is scale by eta. That is, if we say eta is 0.5, that means half is new noise and half of it is going to, half is new and half of it is old. After And then here we add a little random amount of noise in the sample. Any questions?
Did you manage to finish the notebook here? Finish running the notebook here?
Sorry, could you repeat the question? You were breaking up.
Did you manage to finish the running the notebook here?
Yeah, yes, I did, except the last LMS thing didn't work, and I'm still fiddling around with it. With this, he multiplies sigma max. After he moves the value, the size is just 2048, 132, 32. So he's just using that many random values, multiplies by sigma max. So I was thinking, for this, if I just run this guy without my change, it didn't matter. Either one of those give me this error that it doesn't like, for some, it thinks that this guy is somehow, I mean, obviously torch random size, he's a tensor. But then why it says that a tensor is being multiplied by a unit, I still haven't debugged that. But that is mainly this line of code. And I'll go look at, I think he says he took this LMS implementation from that KDiffusion notebook. So I'll just go search in the KDiffusion notebook and probably take the line of code. He has probably modified it somehow, and that modification has gone awry. So, but barring this particular failure to do the sampling with LMS, everything else works.
And how are the FID scores? Is it close to what
these are
okay.
Yeah, these are pretty good, right? 8, 9. That's what he originally gets as well, and you can get as low as 5, as you saw. There's a 5 here. Ancestral 100.5 gives you 5, so that's pretty good when your base score is about 1.3. So 5, 1.3. I mean, pretty darn good at that point.
Yeah, that's cool. I wasn't getting close to this score, so that's why.
Yeah, everything in this notebook works other than this LMS schedule. And LMS schedule, I think I should be able to. It's just a simple something matter with multiplication. I don't know whether you can multiply after you move it to the device or whether you should multiply before you move it. And why the hell it's complaining about multiplying by a unit when it's sigma max is just a fixed thing. I don't know whether this model.device is the issue, and I should just move it, do it this way, device equal model.device. But I don't know. I can always initially multiply it and then move it. Maybe I'll do it in a 2-step process rather than I'll try to do it in a single line. But other than that, everything else works in this. And you can see the results here pretty good.
Yeah, that's cool.
Yeah, so this completes kind of what we'll be fiddling with the entire process of diffusion. Now, in the next 1 or 2 notebooks, he really goes into the detail of implementing because something they have completely deferred is the unit implementation. So we'll talk about super resolution, move on to ImageNet. So we'll kind of move away from fashion and nest and talk in the next couple of notebooks about processing slightly bigger 64 by 64 images, color images, 3D channel images, and then how to do super resolution well and how to implement the unit, which we have not looked at all so far. Some new techniques like attention and so on. Did you have a question, Yuri?
Yeah, so it's a more abstract, and maybe like I haven't listened to last lectures. So hope maybe he actually answers that. So I have a problem I'm trying to solve where I need to generate images or videos that actually have sort of really bad resolution. So real like videos taken with like zoomed in cameras, like a bad condition, stuff like that. And like I'm beginning to think that the only way to use, like, let's say I want to generate it with Stable Diffusion, is to generate good quality images and then blur them out with some other methods. But if you've seen any examples where people would generate kind of low resolution images directly, that would be really interesting.
You mean go from low resolution images to generate
let's say, yeah, no. Let's say I want to generate, this type of fashion MNIST or like a real image. So normally everybody generates very high resolution images, or train networks to do that. But those images are sort of useless to me. I actually need them to be, grainy, blurry. So I was wondering if I need another step to basically make images blurry but it has like a normal kind of noise applied to it, which is like a normal camera noise. But I was wondering if you've seen any examples where people would, generate sort of real images, real life images directly in Stable Diffusion without a step of like high resolution images. It's really not possible.
You should look at even this or the prior notebook, because the noisify denoisify thing that he does should enable you to just go partway through the denoisify process and get blurry images as the output. Because if you don't go all the way in the reverse process, you're kind of in between, where you have some noise and you have some image. You're just getting, and you can choose what fraction you want, right?
The only thing is, yeah, but the only thing is that noise would have completely different kind of distribution and properties.
That's
because.
But then again, the sigma that you're adding in this case is a kind of like a, you have the property of sigma. You saw that in the plot that he showed, right? And maybe you can start off with sigma, which is a noise of your desired property, and see, although at that point, the thing that at least I will lose the ability to do is figure out how the math changes, and whether the math of whether the rules of Gaussian noise is retained, or your noise is something of a different shape to where that no longer applies, and therefore the math they use to kind of base. But you can just empirically play with it and see what results, instead of worrying about the math.
All right, thanks.
So you can use the same framework, but use a noise distribution that's customized, or that's something you want, and see whether the denoisify kind of approach here works for you.
Okay, thanks.
Okay, thanks everybody. We're running late for the Kaggle discussion. So see you all next week. Bye.
Thank you.